So hopefully you can all see my screen right now and me. Great. That's amazing. So uh, in just a few minutes, in 5 minutes, by the way, if you've got questions, feel free to type them in the chat as we go, and then we're going to address them all at the end together. So we're not going to interrupt to take questions. But so I'm going to talk about VPC encryption and some of the problems we saw for that, and some of the big problems and some of the small problems, because I think they give a really good flavor of the kind of challenges we deal with. If you're not familiar with how we do encryption at Amazon Web Services, we've got a pretty thorough encryption stack. You know, we're a big cloud provider, and as you'd expect, a lot of our customers want encryption in all sorts of areas. And we've got client-side encryption tools, we've got key management services, we've got encryption for data in transit, and we've got encryption for data at rest, and so on. But here I'm just going to focus on our network encryption. So we've got network encryption baked into a bunch of places. And we obviously use TLS and SSL and QUIC, just like everybody does. In fact, we have our own implementations of all three of those protocols. And we have a VPN service that uses the IPsec protocol. That's a well-standardized protocol. But we also have kind of in-house custom-built encryption layers. So we've got VPC encryption, where if you launch an EC2 instance, so that's like a virtual machine that is of the right generation and has the right hardware in it, all traffic between any two instances of that type is just encrypted. Customer doesn't need to do anything. There's nothing to enable it. It just happens. If a customer peers two VPCs, so they've got a virtual private cloud in one of our regions and in another, and if they peer those, the traffic between those is also encrypted. And then our physical network, anytime we've got a link that leaves any area that we don't physically control, so like, for example, between two data centers, or even between two cages in the same colo, or across continents, it's protected by physical network encryption. And we had a hand in actually developing this encryption, like, you know, bottom to top, from specifying how the protocols work on the wire to actually implementing it and getting it working in silicon, which, you know, to me, I class as a big challenge. For VPC encryption, this all happens kind of in our physical hardware using our AWS Nitro system. So we've got these embedded cards that are like physically in the box, and they're ARM-based systems that are doing all sorts of hardware virtualization for us. They help us virtualize storage, but they also help us virtualize the network. And there's silicon in there that does AES, you know, at line rate, and can encrypt the traffic as we're sending it. But it, you know, it's not as simple as plugging in a card and buying the silicon and hooking it all together and getting everything to work, right? It actually took quite a lot of effort of designing those encryption protocols, how it's actually going to be laid out on the wire, and formally modeling and verifying all that to make sure that it's secure and that we've got the right security properties. And then a lot of tedious work optimizing that packet pipeline, you know, making sure that we prefetch packets and encrypt them in this really robust, well-optimized pipeline that's not going to degrade customer performance. Not an easy problem. And we pay attention to lots of little details. Like, for example, we have to encapsulate all of this in a UDP packet at the end, so that all of this is friendly with like existing network technologies like float hashing, and doesn't just break existing network assumptions. You know, this is the kind of effort that takes a lot of people over a long period of time, coordinating across a lot of groups at Amazon. You know, we've got Annapurna, who make the networking cards, is part of Amazon. We've got all the folks who design the cryptography, all the network engineers, all the systems engineers and software developers who help with the optimization. So that's like a big problem. But an example of a small problem that we solve, right, is like, well, how do we actually get the keys anywhere, right? So to encrypt all this traffic, we obviously need to have keys that the senders and the receivers share. right? The sender encrypts with that key and the receiver decrypts with that key. At our scale, you can't really do pairwise key negotiation, just wouldn't work. The numbers grow by a square factor, and that's just way too big, way too quickly. So we actually have to get the keys. But we want to follow the principle of least privilege, right? We don't actually want anything other than a device is doing encryption and decryption to know those keys. In particular, we don't want some central magic system that just has all the keys in it, because that would be a very rich target for some kind of attack, right? And then you would never want that. So an example of how we solve this problem in kind of a small way is something we call rumors, right? So what we do is we have separate systems that distribute what we call rumors, or like pre-secret material. And they just distribute this to all of the AWS Nitro cards, which can then combine these rumors into actually knowing the secret key. And I love this example because it's really simple. This doesn't take a lot of lines of code. It's not a hard pattern to do. But it means that if any of our central systems ever have a problem or ever targeted for attack, they actually don't know the secret key. It gives us this really nice isolation property. Many systems and different operators and different peoples and so on would have to be targeted for that secret key to be revealed. Very simple solution. You don't see it in a lot of places. It's an example of like just solving a small problem creatively to get our customers an interesting solution. So that's my big problem and my small problem. And if you've got questions about either of those, I can answer them later. And I'm going to hand off now to whoever's next, because I forgot.
I think I'm next.
Good.
Cool. Yeah. Cool. Thanks, Cool. Let me also do the hardest part of this presentation. This is the screen share. Can you guys see my screen? Yes? All right. Yep. Cool. I'm sure you guys have questions about Cole's presentation. Start posting them in. Don't hold on to them. You can put them in the chat box, and we will actually come to them towards the end. I'm Ali Khayyam. I'm actually the senior manager. I'm the only person who is not a principal here. So I have a serious imposter syndrome thing going on right now. So I'm actually a manager at AWS. I've been here about 3 years. My team is really split into two halves. One of them is internet measurements, and the other one is SDN controllers. And I'll talk about both of these and how they work together for AWS customers. Start off with a fun fact. This is the first slide deck I've built in 3 years. We don't do, if you don't know this already, we don't do any slides in AWS or Amazon in general. We just do nothing. It's all us. That didn't go so well.
We can hear you now, Ali.
All right. Sorry about that, guys. Yeah, okay. Cool. Can you guys see the screen again?
Yep.
Yes? Okay. So yeah, I was saying that these are these 6-page narratives that we write are very similar to research paper, very specific format, and very data-driven. Very similar to research paper. The only difference is that you actually get your peer review right there and then. So you bring it to a meeting, the first 20-30 minutes, people just read the doc and the 30 minutes of discussion, and you get your peer review there and then as to whether this is getting accepted or rejected. So it's a pretty interesting concept, and I enjoy it. It's liberating for me not to have to do PowerPoints. Okay, moving on to the AWS WAN infrastructure. Another fun fact, the AWS or Amazon generally has a different name for everything. We don't call this WAN, and we don't call the controllers SDN. I guess because we start way before these things become super cool. So we have a different name for all of these things. But yeah, I'm trying to use terminology that you guys would be familiar with. Our WAN infrastructure is really divided into 4 different components. One of them is regions, right? Our AWS regions. POPs, and we have hundreds of these POPs as well. POPs are of 2 types, so we have 2 different distinct types of POPs. Standardized, but the 2 different types. One of those is actually what connects a region to the internet and to the rest of the world, and the other one is what connects generally our edge-hosted services. So an example of an edge-hosted service would be CloudFront, which is our CDN, or S3, which is our storage layer, or Global Accelerator, which is our global load balancer, and Direct Connect, which is our private connectivity that Amazon provides from your private data center into AWS regions. So we've got these hundreds of POPs, 24 regions. All of these are connected through, the connectivity is provided through a global backbone. So all east to west traffic across regions from the POPs coming back into the regions goes over our global backbone. And eventually, whenever we have to deliver bits to our customers, they go over the transit and peering connection. So we've got a huge transit and peering footprint all across the world with many different providers. And that's really, that footprint is what my team focuses on. And the technologies in my Oh man, I should be talking about the internet. The internet is angry with me for saying that it's just broken. So yeah, I need to bring some of my controllers into my place. If this breaks again, I'll probably just move over to my my mobile network, because the wireline one does not seem to be working very well. But yeah, internet environments, we do 3 types of internet environments. We have synthetic environments going from our regions of POPs towards customer destinations on the internet. We have similar kind of synthetic environments coming into our regions and POPs. We also have passive environments where we look at other services and what they are seeing. So something like S3 or CloudFront, and look at TCP socket parameters to see, all of a sudden if they're
This has become a live demo of network reliability.
Hey, John, do you want to take over and we can come back to Ollie in a few minutes?
Absolutely. Give me 1 second.
Hey guys. Okay. Hopefully AT&T serves us better. Sorry about that. All right. Can you see my screen now?
Yep.
Okay. If this breaks again, this is bad karma, guys, because I really switched over to the AT&T network. So let's see how this goes. So I was saying we had synthetic environments, data plane environments going from regions and POPs to destinations and coming back. We have passive environments that we look at other services and what they are observing for internet impairments. And then finally, we also look at control plane. And that's a very important piece of our monitoring story. So with all of our transit and peering footprint across the world, we have a very unique vantage point to look into what the world is seeing from an Amazon prefix perspective and what we are seeing from the rest of the world. We also have feeds, BGP feeds coming from external networks, intermediate networks that connect us to our customers that tell us if there's any anomalous behavior of Amazon prefixes being propagated on the internet. So active and passive, control and data plane, all of these are part of this. These environments actually are what inform our SDN controller. So this is the foundation. And whenever in steady state, we see a path that could be better for a particular prefix on the internet, that is vended to the SDN controllers, or if there's a fault that is happening on the internet, what is the fault, where is it happening? That information is fed into the SDN controllers. And SDN controllers are then the ones that actually make a decision about, where traffic should be rerouted to, in steady state to just provide the best performance to our customers, and under a failure or a fault, I'm like, where should it be rerouted to? SD controllers have actually pretty interesting task because they have to optimize traffic across many different dimensions, like availability, reachability, then also performance, which is latency, jitter, throughput, dollar cost of routing at our scale. It's actually a pretty important factor to consider as well. And finally, business constraints like commit rates or those things also have to be factored into this thing. As you can see, some of these are actually even conflicting with each other. So your most performant network might not be the most available in certain geographies. If you're getting higher, the best latency, generally the cost also goes up. So this is a very interesting mix of, how do you optimize across these dimensions that actually be competing with each other. The goal, these things work together. The goal is to optimize the connectivity experience of our customers. And this is a full feedback loop. So the SD controllers, when they make a decision and enact it in the network, they actually go back to the internet measurements and see if the decision that they took is actually making the connectivity experience better. The problem that they were trying to solve, is it really even solved, and or is there any other connectivity improvement that is still impacting the customers? I'll talk briefly about challenges, technical challenges, the big ones, lots of data on the internet measurement side, lots and lots of data that has to be ingested globally, that has to be collected, ingested globally from our own services, external services. Then we have the internet measurement team has to make a lot of inferences on the data. There's a lot of information theory, machine learning that happens over there on, there is something wrong on the internet, what is wrong and where is it wrong? All of those sort of like the temporal and spatial elements have to be fed into the SD controllers. The SD controllers make routing decisions optimized across multiple dimensions, as we talked about earlier. And then SD controllers are also responsible for implementing these decisions in this global network with consistency and correctness. So it has to be, the decisions generally start off with a local context, but they need to be propagated all over the world. And just making sure that any decision that we're making is not just moving the problem around. So there's congestion somewhere, you just don't want to move it around and keep oscillating, just moving that congestion around. So it has to be consistent. They have to be correct in terms of, when you make a decision, you're not overriding it by some other component. We got multiple SD controllers, which each become an application on top of the same substrate of foundational services that we have. But you need to make sure that they're not sort of tripping on each other's toes. So there's some correctness guarantees that we have to provide. And eventually, like I said, it's a full feedback system. So you go back to the internet measurements to see that you actually are providing, solving the problem that you're trying to solve, whether it's to put traffic on the most performant path or to bypass impairment that you just detected on the internet. The interesting part of it is this all has to be done in real time. So real time is like 5 minutes or less. Everything that I mentioned over here, we want to do it very, very quickly. And we want to make those decisions and enact them in the network very quickly as well. My last slide, I want to talk about my team also in terms of people. So all of my team are generally basically 3 different types of skill sets. One of them is software engineers. These are your core strong distributed systems and systems people, algorithm data structures people. Then you got scientists. You have 3 different types of scientist families in Amazon, and reach out to me or Kelly or Jarby for about what these families are. But there's 3 different types of scientist families. But these are your sort of mathematics and statistics and machine learning folks, which are making the algorithms and proving them with production traffic that these are things that that would actually work in production the way we want them to, within the time and space constraints that we have on these algorithms. And finally, we've got network engineers. These are networking experts who would tell us, how a particular decision that we're making be impacted and implemented inside of an ASIC, let's say, on a particular networking platform. What are the existing protocols that are available or options that are available to implement these decisions, and which one is the right one? And that can have a big impact on what the scientists are developing or what the software engineers are implementing. Here's my sales pitch. SIGCOMMers are right squarely in the middle of all of this. You guys have all of these expertise. We already got a few of you in our team, and would love to have more. So this can't end the presentation without a sales pitch. So fun fact, and with a fun fact, since we started talking, maybe more than this, because I was supposed to take 5 minutes, but I think I took more. So nearly 600 million internet measurements have been collected since the start of this presentation by our infrastructure. Please feel free to post questions, and I will hand it over to John.
Thanks, Ali. Stealing some of my thunder there.
I am.
I'll forgive you.
Plagiarized
Okay. So, can everybody see my slides?
Yep.
Great. So thanks, Ali. Yeah, I'm John Evans. I'm a network development engineer. I've been at AWS for a couple of years, and I focus on network availability and performance engineering. And I'm going to try and highlight some of the challenges that we try and solve in AWS in that area. Now, we deal with a lot of data, so I thought I'd measure the progress through my slides in terms of the volume of data that we're generating in the network at the moment. But just to give a little bit of suspense, I'm not going to tell you what the units are until we get to the end of the presentation. So we're going to start on 0, and then we're going to incrementally work through the presentation, and then I'll do the big reveal. So, whoops, my slides seem to be changing on their own. So what problem is it that we're solving? And I'd express it in terms of answering 2 questions. The first one is, how do we measure the network performance we're delivering in terms that represent our customers' experience? That sounds relatively straightforward, but we've got many different customers with many different services. We have them in local geographies, in spread geographies, doing things that are real time, doing things that are offline. So that is a It sounds like a simple question, but actually it's fairly non-trivial. And then once we've defined it, how do you measure that globally at scale? The second question that we try and answer is, once we've got that definition, how do we maximize our network's availability at delivering that defined performance? And this is a data analysis problem, and we solve it by sorry, my slides progressing automatically. So we solve this by analyzing the huge volumes of data that we get from the network. We have different systems of producing data. So passive monitoring, which we get from the devices themselves, active monitoring from synthetic traffic that we put on the network in order to measure the performance. We have different types of data. We have metric data, which expresses performance. We have event data that expresses changes of state. We have flow data that expresses that describes traffic information. I'm going to, I guess, orient this around metrics, but if PowerPoint will behave. So after we've collected that data, we have to transform it in order to make it usable, but then we look for indications and signals that the network's not performing as we expect. And so this is where we're really looking for anomalies and looking for anomaly detection in that data in order to give us some indication of where things aren't delivering on that performance. Now, as you can imagine, with a lot of data, you get a lot of anomalies. Anomaly doesn't mean that you've got a problem, but it may. And so in order to make sense of the anomalies that we generate, we then have to correlate those and try and identify, in all of that information, try and identify what's causal. So we have systems that deal with anomaly detection. We have other systems that deal with correlation and causation, and the outputs of those essentially are actions. And we have other systems that take those actions, take those triggers, and actually look to solve the problems on the network without causing impact to our customers. So let's give an example. Let's imagine that we've got a network device. We detect that network device is having a problem, which may be through passive monitoring, through active monitoring, or a combination of both quite frequently. We would proactively take that device out of service. We would shift the traffic away from it before we do, so that we don't cause customer impact. We'd then take the device out of service. We'd then remediate the problem. Once we've remediated the problem and confirmed it's working, we'll then bring the device back into service and shift the traffic back onto the device. So our goal, in all of this is that we're able to try and detect problems before they're customer impacting and try and fix them without a human actually being involved. So now the big reveal. I mentioned we do that by processing the data we get from the network, and in the time I've been talking to you, if I'm keeping to time, we've collected 6 billion network observations. So put another way, that's 6 trillion network observations in a day that we process. And obviously that creates challenges. We're fortunate that we've got a set of services that are scaled to deal with that. AWS Glue, AWS Athena, and that also that we've got a good ecosystem of data scientists, research scientists, network development engineers, and software development engineers in order to try and tackle these problems. That was everything I had. Look forward to your questions. Thank you.
All right. I think next up is me. Let me also try to make sure I get this part right. And let me take over John's screen sharing. All right. Hopefully you can see my screen. Hi, my name is Andrew Dickinson. I'm going to be talking about some of the challenges of designing a software-defined network for Project Kuiper. If I can advance my slides, that would be wonderful. Before I jump into talking about Project Kuiper, let me tell you a bit about myself. I started at Amazon in 2004 when I was fresh out of college with a degree in computer engineering. In 2007, I joined a little project working on cloud computing called Amazon EC2. You might have heard of it. On the EC2 team, I had an opportunity to design and build a lot of the technology that makes Amazon Virtual Private Cloud, or VPC, possible. Work with Colm on some of that stuff. The scale of EC2 makes problems like VPC very exciting. There's no textbook solution for how to build a software-defined network that can operate at the scale that we're operating at. In fact, I believe that the VPC network is the largest multi-tenant software-defined network anywhere in the world. Now, building a system like that at that sort of scale, it's a team effort, and I've had a chance to learn from and work with some of the smartest people in the industry. After working on VPC for more than a decade, I was longing for those early days in EC2, and I decided to join Amazon's Project Kuiper. If you're not familiar, Project Kuiper is Amazon's long-term initiative to provide low-latency, high-speed broadband connectivity to unserved and underserved communities around the world by launching a constellation of low Earth orbit satellites. We've heard so many stories lately about people who are unable to do the job or complete schoolwork because they don't have reliable internet at home. And there's still too many places where broadband access is unreliable or where it doesn't exist at all. Kuiper is going to change that. Projects like Kuiper are one of the things that I love about Amazon. It's bold and ambitious. Building satellites and launching them into orbit requires a team of highly interdisciplinary engineers. I'm working with people with specializations in solar panels and batteries, thrusters and space mechanisms, microwave RF and antenna designs. Project Kuiper depends on all of those specializations to be successful, but our customers don't see them. Our customers don't care how efficient the solar panels on our satellites are, or they don't care how smooth the thrusters on the satellites are. They care about the network. We want to delight our customers with a broadband experience that's indistinguishable from terrestrial broadband offerings. Actually, for many of our customers, we want Kuiper's broadband offerings to be better than what they can get from a local terrestrial ISP. The Kuiper network is a software-defined network, but we've got some unique challenges that most SDNs don't have to tackle. For example, with most software-defined networks, the network itself is relatively stable, and the engineering challenge for that SDN is how to get packets from one point to another across that topology. Project Kuiper has an extra twist. The network itself is physically moving. Our satellites are in low Earth orbit. They're zipping by at 27,000 kilometers per hour. To provide continual coverage to our customers, we plan to launch over 3,200 satellites and a constellation around Earth at altitudes around 600 kilometers. At those speeds and altitudes, a customer can see any given satellite for only a few minutes at a time, and they'll need to continually have their network connection hand off from one satellite to another. So let's look at that in a little bit more detail. At 600 kilometers above Earth, we're dealing with at least 2 milliseconds of flight time between the satellites and our customers. And that's just physics due to speed of light, or RF in this case, over that sort of distance. We want to keep latency and jitter low. So let's think about this transition from one satellite to the next. Even if the outgoing satellite stops transmitting at the exact moment that the incoming satellite starts transmitting, the customer's equipment at their home needs to keep listening to that old satellite for a few milliseconds to receive the data that's in the air between the old satellite and that customer equipment before that equipment quickly turns and starts receiving data from the new satellite. Now, that's crazy, but let's keep going. We also need to handle uplink data from our customers. So during this transition, it'd be really nice if that moment in time when the old satellite stops transmitting towards the customer, if that aligned with the time when the satellite stops receiving from the customer. What this means is that we want our customers' equipment to start sending data to the new satellite just ahead of that transition time, literally shooting into the dark at the satellite before it gets there. This is just one small example of the challenges that Amazon faces on a daily basis. And I love these sorts of challenges, and I love that Amazon is willing to take bold and ambitious bets like this. Thanks, everyone. Next up, we're going to take questions. I see that you've already been typing them in the chat.